Okay, welcome to this video. We're going to start on module 6, and this is a video on the structure of benzene, and specifically we're going to look at disproving Kekula's model. So Kekule identified that we had this special carbon compound that appears, or hydrocarbon compound, appears in a lot of molecules, and it worked out the formula was C6H6, this compound. So it took him a few years to figure it out, what the actual molecule was. And he dreamt one night of a snake eating itself. And he had this idea that it was a ring structure. Now he put 6 carbons in a ring, and now that gives each carbon bonded to each other, so they're all bonded twice. Each one then has a hydrogen around it, which I'm not going to draw in, but every single one's got a hydrogen. And then every other bond he suggested was a double bond, and that then fit, and that had 6 carbons with 6 hydrogens, each carbon then bonded 4 times. Now there's a few things that we now know that are wrong with this particular model. So first of all is that off slightly. Its reaction with bromine. Now, if we take something with a double bond, I'm just going to put a double bond here, and a bromine molecule comes near it. I'm sure some of you watching this will be like, oh, I know what happens here. But because this is an area of dense electrons, the electrons in the bromine molecule get pushed to one side, creates a dipole. So these electrons around this bromine, this bond, get pushed over to this bromine, and that becomes slightly negative, and this becomes slightly positive. And this is all due to the fact that this double bond is a dense area of electrons, and then it's a different colour. Pi bond breaks, we get a reaction occurring. Bromine gets taken in, this becomes a bromine minus, and that can then join on again, and we get a reaction. So if we took Kekula's structure, put a double bond in, we'd then expect this to do exactly the same thing. When bromine comes close, we'd expect a reaction. And that should happen in Kekula's structure, but it doesn't in benzene. So the first reason why Kekula's structure may be wrong is that it doesn't react with bromine, or it doesn't decolorize bromine. Common reaction, this will be a yellow solution if we have bromine to a double bond, and then when it reacts and the bromine joins on to the single bond that is then left here, it goes from yellow to clear. Now if we add bromine water to a benzene molecule, we don't get that decolorization. Later on we'll see how we can make bromine react with a benzene molecule, but we have to add something else to it. So that's the first reason. The second one is the bond length. When we have a look at the bond lengths, a carbon to carbon bond is approximately 154 pm. So very, very small. But a carbon double bond length is 134 pm. So even smaller. So what we'd expect to see in the structure is small double bonds bonded to long single bonds. And we'd get an irregular hexagon. My drawings are pretty terrible. But what we actually see when we look under an electron microscope is a perfect hexagon. So again, we can't have double and single bonds together to form a perfect hexagon, because single and double bonds aren't the same lengths. So 2, second reason is the bond lengths are all the same in benzene. Suggesting something in between the two. And the third and final reason is its hydrogenation enthalpy. If you react benzene, let's do Kekule structure, sorry. Very simple. If we react this structure with hydrogen, so plus H2, it's going to go to cyclohexane. So cyclohexene plus H2 goes to cyclohexane. And that gives off mm, 120 kilojoules per mole. So an exothermic reaction, the enthalpy is 120 kilojoules per mole. So what we'd expect to see then, if we got Kekule structure of benzene and reacted it with 3 hydrogens, molecules, to form cyclohexane. So we're just doing the same reaction, but this time with 3 of them, we'd expect to see an enthalpy equal to minus 360 kilojoules to mole. It's just this reaction 3 times. The energy given off is these hydrogens joining on. Or, well, in here, 2 hydrogens join there. In this one, every single carbon will get an extra hydrogen. So 3 times more than this one. We'd expect that, and that doesn't happen. Instead, our benzene plus 3H2 to form this cyclohexane is actually minus 208 kilojoules per mole. So we get this change in enthalpy of hydrogenation that we wouldn't expect if Kekule structure is right. So number 3 of our 3 reasons is the hydrogenation enthalpy is a lot lower in benzene than you'd expect from Kekule structure. So that are our 3 reasons. Got reaction with bromine, bond length, and hydrogenation enthalpies. So we've looked at Kekule structure, and it's still up for debate what benzene really looks like. The more accepted model now of benzene is nice, all equal bond lengths. Each one of these carbons still bonded to a hydrogen like Kekule's, but they don't have a double bond. Rather than overlapping p orbitals to form double bonds here, all the p orbitals overlap, and each carbon gives 1 electron into a central ring. And we get 6 electrons then, and they're kind of above and below. So you'll be able to see 3D structures of this. I try and draw 3D structures, and they're absolutely terrible. So I'm not going to even bother because it'll just confuse you even more. But they're above and below this carbon. We get a nice ring where all our electrons live, and they're very stable, very happy there. If we were to draw it out and show the 6 carbons, each with 1 hydrogen. So each is bonded 3 times, and then they've got together, each one's given their final electron, all sits in the middle in a delocalized ring. And that is how we accept now benzene has. And so this isn't strong enough to decolorise bromine. So when bromine comes close, it doesn't create a dipole. It has all the same bond length, because they're all the same types of bond, and then hydrogenation enthalpies to add another hydrogen on to give as much energy off as if you did it through with an alkene. So this one fits a bit more those three reasons we saw earlier.